Hi guys, I'm Sachin. I'm going to talk about cryptography and blockchain. So, in this session, we are going to learn about how cryptography acts in blockchain. Exploring how cryptography principles enable this decentralized system, immutable ledgers, and trustless verification in modern blockchain architecture. So, before going into the cryptographic part, we have to learn what is blockchain. For that, we have to get into the main core concept of blockchain, which is distributed ledger. Distributed ledger is the basic core idea of the blockchain. So, what is a distributed ledger? A distributed ledger is a database replicated and synchronized across multiple independent nodes in a network, eliminating the need for central authority. Each participant maintains an identical copy of the transaction history, ensuring transparency and resilience against single point of failure. So basically, the distributed ledger is we instead of keeping a centralized organization, we distribute the power to every node. Every node in a system would be having equal amount of power, and every node would have the transaction history of everything. So basically, it would be and open source to everyone, and everyone can know what it is all about, but no one can tamper it since it's not centralized. It's with everyone. If you tamper, it would be only tampered in a single node and cannot be done in all other node, which makes it really impossible to tamper in distributed ledger i- if if the attacker doesn't take more than 50% of the network. So let's see what's the role of cryptography. Cryptographic techniques bind blocks together. The blocks that we are talking here about is the node which I discussed in the distributed ledger. So, cryptography techniques bind blocks together chronologically, creating an immutable chain. Hash functions like each block to its predecessor, while digital signature authenticate transaction. This mathematical binding ensures that any tampering is immediately detectable across the entire network. So basically, we use hash function in this thing where we connect each block, that is each node. Uh, Each block contains the hash function of the previous block. Thus, if a person tampers a block, its hash value would change, which would which can be predicted in the next block because of the hash function. Thus, hash functions plays a major role in the tampering and in the blockchain. So we use digital signature to authenticate transaction. So basically, in each node, we capture transaction, and only if we can authenticate that a person A did that, which we can do only with the help of digital signature. And digital signature is also a cryptography thing. So these all cryptography things add up to the immutable, detectable entire network. So, cryptography techniques. Code as I already told, hash function uh, computes the hash value for each node. So deterministic algorithm producing fixed length digits from variable input. SHA-256 for Bitcoin and another KAC-256 for Ethereum. Transform data into unique fingerprints, enabling rapid tamper detection and block verification. This hash function. basically takes an input of any size, whether it may be an 1 bit or 2 bit or 3 bit. But whereas SHA-256 would return as a 256-bit output. And since it is variable length and fixed output, it is really hard if we give an output value and get the input value to predict the input value, which is very very hard. Thus, this hash function plays a major role in the blockchain. Digital signature. As I said already, digital signature is what proves who did the transaction. So basically, cryptographic protocols proving authenticity and non-repetition. Elliptical curve digital signature algorithm signs the transaction using private keys, allowing verification with corresponding public keys without revealing the private keys. Digital signature is right now everywhere. We use DigiLocker and many more things, and everything comes from the DigiLocker. Basically, we sign a document with our private key. The private key would only be checked by our public key, and we cannot find our private key using the signature. Thus, anyone in the world can verify that it was signed by me, but no one can re-sign it like me. Thus, digital signature helps the blockchain to be legitimate. Public key cryptography. Asymmetric encryption using paired keys, private keys, sign, and decrypt data. Public keys verify signature and encrypt messages. This asymmetric enables secure multi-party interactions without prior key exchange, foundational to blockchain transaction. So, as I said before, uh, this blockchain thing, we get we get to have private key and public key. We, in this, private and public key are different. This encryption is called asymmetric encryption. That is, we sign something with private key and we unlock it using a different key, which in this case is public key. This asymmetric encryption also helps us to the helps us on the blockchain. These three are the core cryptographic techniques that we use in the blockchain. Hashing and block integrity. Each block contains the hash of the previous block address. As I said before, to find an tampering, we can only find it on if we have the hash value of the previous block in the next block. So if someone changes the value in the previous block, it hash would be changed. Thus, that hash and the hash that was previously defined in the next block should be same. If it changed, then we can know that tampering has been done. Modifying any historical transaction changes its block hash. It breaks the link to all subsequent blocks, as I said before, immediately signaling tampering to the entire network. This elegant mechanism ensures immutability without requiring central oversight. This thing can be easily found out by every node with just a single line code if block. Thus, it doesn't require an overview of a central organization. Tamper ticket detection. Altering a single byte in a block changes its hash completely due to avalanche effect. This cascading invalidation makes retrospective fraud computationally infeasible in mature blockchain with significant computational work invested in subsequent blocks. So basically, uh, a, a bit change in a block would change over the overall output of the hash. This thing is called avalanche effect. Due to this, it's really effective if we change even a extra 0 to a transaction. Thus, it is very, very tamper detection friendly. Public key cryptography in blockchain. So, we use elliptical curve cryptography. Basically, what is elliptical curve cryptography? We define an elliptical curve and mathematical graph curve, and we get all the points of the curve, and we talk, we send the message and receive the message in terms of points in that curve. The private key, the public key, the message, the ciphertext, everything that we refer in this thing is referred in as a point in that curve. What makes it so special is that doing a mathematical computation is much or more easier when compared to doing graphical computation. So Bitcoin and Ethereum employ this and technique which shows 256-bit security. ECC offers superior security compared to RSA, enabling compact keys suitable for resource-constrained blockchain environment while maintaining cryptographic strength against known attacks. The main thing about blockchain is it should be updated every second. We can't be having a very big key for a blockchain. Thus, that would make it really difficult to update the node in everything. So, having a very less amount of data is effective. Thus, RSA is also a good protocol, but it requires a very huge uh, number, whereas ECC provides the same level of security with very small number. Thus, ECC in our case serves better. As you can see, the public key is also a point on the elliptic curve. Digital signature. So basically, we hash an transaction and sign the transaction with our private key, and we attach the signature to the uh, transaction, and we afterwards anyone in the world can verify that using the public key that we publicly expose already to the world. This thing helps us to do the legitimate transaction. Consensus mechanism. Mm, Basically, in blockchain, consensus mechanism is what proves that every node has a equal or same data. Thus, maintaining a same data throughout the network is essential, for which we have consensus mechanism like POS and POW. POW, proof of work. Participants compete to solve cryptographic puzzles by repeatedly hashing block data with different node value. Finding an hash below a target difficulty requires substantial computational effort. This work secures the network. Attacking the blockchain would require controlling 51% of the computing power, economically infeasible for established network. So, proof of work. Mm, Everyone would get the new transactions that are done in the blockchain, but not everyone can release an block. If everyone released a block, there would be an huge hectic for everyone. Thus, what we do is we solve a cryptographic puzzle, a really difficult cryptographic puzzle to find a nonce value. These nonce values are big prime numbers which we cannot predict using some algorithm or anything. It's basic random guessing. So all node would try to find the nose value, and the first one who tries to find the nose value would be able to create the block. Thus, this thing makes it a proof of work. Since everyone does it, the one finding the nonce value can afterwards show to everyone and prove that he solved it. That thing is called the proof of work. So, proof of stake. Validators take cryptocurrency as collateral to propose an untested block. Cryptography sortation selects validators probabilistic based on stake. This mechanism allows incentives validators lose stake for misbehavior, making attacks economically irrational while reducing energy consumption compared to peer. In proof of work, everyone would try to solve the cryptography puzzle, which makes it really computationally heavy. Whereas proof of stake, what we do is we voluntarily bet, we voluntarily invest some money or mm, mainly we keep it as stake. And if if we do anything wrong, that money would be taken away from us. Thus, only a small part of the group would be able to create the block, which makes it really efficient. Cryptography hash puzzle and mining. Miners construct block candidates containing pending transaction. They increment a node's number and repeatedly hash the block address. The current difficulty sets a target minus must find a node's position as numerically less than the target. Bitcoin adjusts difficulty every 2016 blocks to maintain approximately 10-minute block times. So yeah, it's basically the same thing I have told before. Only with the mining we can prove that the no tampering is done. Otherwise, there would be no one to check it. So what we do is we solve a cryptographic puzzle and find a nonce value and prove that to the world. So Bitcoin, what it does is this nonce value, we there's a thing called target, which basically uh, shows the difficulty level of the thing. Having more number of zeros in the difficulty would increase the probability of the finding nonce is reduced. So Bitcoin adjusts this after every 2016 blocks, maintaining the difficulty as the upcoming generation. Since the computational power is getting increased day by day. Privacy enhancing cryptography. Zero knowledge proof. Enable proving knowledge of a value without revealing the value itself. A prover convinces a verifier of transaction validity without disclosing amounts or addresses. Zcash implements for confidential transaction while maintaining anonymity. Yeah, so we can prove something that we have without actually showing it. That's what we are telling in the zero knowledge proof. Uh, in the same way, if we sign a document, but actually we do not tell who signed it, who did it, we just know it's unverified. In the same way, it is yeah. Ring signature. A transaction signer creates a signature that could originate from any of the member of the group. Monero combines ring signature with Stull's address, making transaction sources statistically indistinguishable. This sender identify while remaining cryptographic verifiable. Homomorphic encryption. allows computation on encrypted data without decryption. Computations performed on ciphertexts yield results that decrypt to identical outcomes as plaintext computation. This enables privacy preserving smart contracts, where state calculation remain encrypted on chain. Smart contracts are something like uh, it's an inbuilt thing we have in every node. So basically, if I send in 1000K without the user manually returning the 1000 rupees, what we do is we write in smart contracts, and when the person gets the 1000 rupees, it automatically reverted back. It's an automated process which happens, and no one can change it or move it. That's how smart contract works. So real world application and future horizon. Right now we are using SHA-256 hashing and elliptical curve in Bitcoin. And in Ethereum we are using SEC 256 and same elliptical curve in Ethereum. Hyperledger is a open source blockchain builder kind of thing which uses elliptical curve for many purposes. Monero is used for ring signature and stealth addresses. The challenges that we may face hereafter. Post-quantum cryptography. Quantum computers are not like the computers that we have now. It is much more efficient. The main thing about elliptical curve is hard to computation do right now because it is computationally heavy. But if quantum computers comes, it would be an easy task for the quantum to break it. Thus, elliptical curve won't do the proper digital signature. We have to see for another alternative. Scalability and key management. The main thing about this is every node should be updated within minutes. This updation should be instant. It cannot be late. For the huge population that we have, for every transaction that we do, we cannot update it in the blockchain because for each second it's in billion amount of that thing we are doing. So if we cannot update that much in the blockchain, that is the only scalable issue that we have. So thank you for listening. Thank you.